Today we're going to learn about the difference array. And okay, so in case you missed it in general, we're going to be taking a break on the 10th, on the 17th, and we're going to come back on the 24th, possibly with a contest. I'm assuming people would want the contest more on a Wednesday than on a weekend. And after that, we're going to be starting dynamic programming. And so difference arrays is going to be our conclusion to our simple algorithms and data structures unit. So yeah, so let's jump right into this problem right here. So this problem, I'm going to summarize it. It says this person, she has n tasks, which each have a starting point and an ending point. And each of her machines can do one task at a time. And she wants to know how many machines she needs to complete each task. How many machines she needs to complete all the tasks. And you might notice that this problem is very similar to what we put on the warm-up contest. So basically the same idea. In the warm-up contest, the problem 2 said that Evan had volunteering events, and he wanted to recruit volunteers to attend each event, and each of them also had a starting and ending point. And we can see the constraints on n are somewhat similar. So to get a clue to how we can solve this problem, let's go back to how we solved this problem in the contest. So if we open up the solution to the problem, we said that events at I stored the number of events on day I, and essentially what we did was we reduced the problem to adding 1 to events at j, where j is the day. And so from the starting point to the ending point, we would add 1 to events at j. And in the end, we're going to go through all the days and find the maximum number of overlapping events at any given point. And this would certainly work for this problem that we're doing, except if we go ahead and calculate the time complexity of the solution that was intended for the contest problem, you'll notice that there's this very special constraint that makes this solution possible. So if we look here, it says x and y would be no more than 10 apart. And so in other words, y minus x plus 1 is less than or equal to 10. So you know that this for loop will never run more than 10 times. However, in our problem here, there's no such constraint, right? You know that the starting point can go all the way to the left down to 1, and the ending point can go all the way up to 10 to the power of 7. And so if we were to calculate that, if there was no constraint on that, we would have n tasks, so that would be 10 to the power of 6. And if we were to add 1 to all the numbers from 1 to, or all the indices from 1 to 10 to the 7, then we would have 10 to the 6 times 10 to the 7. And that would be something like 10 to the 13. And so you know that's way bigger than 10 to the 8, which is the approximate number of operations that C++ can perform in 1 second. So you know that adding 1 to, whoops. Okay, so you know that adding 1 to each index of the days will not work for this problem. So how can we perform this range update in sublinear time? And that's where the difference array comes in. So what do difference arrays do? It performs range updates in constant time. And how does it do that? So it performs an operation, so in this case it would be addition, to the starting point of the range, and then it performs the inverse operation. For example, the inverse of addition is subtraction. So to the exclusive ending point of the range. And then when we calculate the prefix sum array of this array that we were updating, we're left with the updated array. Now, this is a little confusing right now, but let me demonstrate how that works. So we have the sample right here, and as I go along, keep in mind that The first number is the starting point, which is inclusive, right? And the second number is the ending point, which is exclusive. So I see that it's never going to go past 8 days, so let me just draw 8 circles, or actually 8 zeros is what I meant to say. So each of these represents the number of events that, the number of tasks that are going to be happening on that particular day. Okay, so, and if there's a task going from 1 to 3, that would be these two elements excluding 3. And so we want to perform a range update on these two indices. Now, instead of doing a for loop on these two indices, what we're going to do is, as we described here, we're going to perform the operation at the starting point and then perform the inverse operation to the exclusive ending point. So what I mean by that is, if I want to add 1 to this range right here, I'm going to add 1 here, and I'm going to perform the inverse of adding 1, which is subtracting 1, at the exclusive ending point. And I'm going to subtract 1 here. Everything else stays the same. Now watch what happens when I calculate the prefix sum array of this array. I have 1, 0 plus 1, that'll be 1, -1 plus 1, that'll be 0, and the rest I have zeros. So we can see that we actually have 2 1s updated to this range. So we added this range by 1. And what we did, all we did was perform 2 operations. Let me do a couple more updates just to show you. Whoa, okay. That was not intended. I'll just fix that really quickly. Okay, so now let's update the range 1, 4. And again, we're going to do the same thing. We're going to perform the operation on the first, on the starting index. So we're going to add 1 to position 1. So that becomes 2. And everything else stays the same. And at the ending index, which is exclusive, we're going to do the inverse of adding 1, which is subtracting 1. And now we're left with this. Now let's do one more before we calculate the prefix sum array again. So it's from 2 to 5, we're going to add 1 to the starting point, which is 2. And at position 5, which is the exclusive ending point, we're going to perform the inverse, which is subtracting 1. So this is our array right now. And now let's calculate the prefix sum array of this array so we can get our updated array. So we have 2, 1 plus 2, that's 3, -1 plus 3, that's 2, -1 plus 2, 1, -1 plus 1, 0, 0, 0, 0. Okay, so we can see that we're left with 2, 3, 2, 1, and the rest are zeros. And now let's just draw out these tasks. So from 1 to 3, that would be one interval. From 1 to 4, that would be this interval. And from 2 to 5, that would be this interval. And we can see that our array was updated correctly. So at this point, we have 1 and 2 overlapping. We have 1, 2, 3 overlapping for this. We have 1 and 2 overlapping, and then we have 1 overlapping. And how you can kind of imagine this is, wow, that's not what I wanted to do. I'll just fix that really quickly. Okay, so what you can imagine that we're actually doing is, since we are going to be taking the prefix sum array of this array later on, whenever you add something or whenever you do something to the element, you're not only applying it to the current index, you're applying it for everything that's going to go beyond it, right? Because the prefix sum array is cumulative. So as we go left to right in the array, it's going to take this element and it's going to keep applying it to everything that's after it. And how this works is that if you apply the operation to the starting index and you apply the inverse operation to the exclusive ending point, what that's going to do is, first of all, that's going to update these two at least, which is your intended range. And then when you perform the inverse operation, that's going to cancel out with the operation itself, right? So you know that these will cancel out, so that nothing will happen to this, and nothing will happen to this, and nothing will happen to everything that's beyond. And so in the end, what you're left with is that you just updated whatever's in front. So you can almost think of it as everything we do to an index, we're doing to the entire suffix. And so therefore, if we want a specific range, you do it to the entire suffix, and then you do the inverse to the suffix that you don't want to change. Now, before I go ahead and implement difference arrays, are there any questions about what I did? Wait, okay. I thought I was muted. Okay, if there are no questions, I'm gonna go ahead and implement this. So, okay, so we know that our updates are gonna perform over the days, and the days go up to 10 to the power of 7, so we need a difference array of length 10 to the 7. So the number of tasks is n, and let's name our array diff. Okay, so let's take an input, and for each of the tasks, let's take in the starting point and the ending point, so SF. And what we're going to do is increment the starting point and decrement the finishing point. Notice again that they made the finishing point exclusive on purpose, so it would make it easier for us to implement. But if they were inclusive ranges, then you would need to add one to make the ending point exclusive, right? And that's it. This for loop is all we needed to update this array. And now let's take the prefix sum array of the difference array to get our final array in the end. And actually, no, I'm just going to do that, yeah. So remember here that we have to loop to 10 to the power of 7 so that we actually loop through all the days. And that part initially tripped me up because n only went up to 10 to the power of 6. So if you loop to n, that would not be enough. Okay, and if you were here, I believe last week. No, the week. Okay, if you were here 3 weeks ago, you would know how to compute prefix sum arrays. And that's very simple. It's just diff at I plus equals diff at I minus 1. Okay, and now we have diff at I storing the intended element at each point in the array. And now all we need to do is just extract the maximum, because it asks for essentially the maximum number of overlapping tasks at any given point. So let's have a variable answer. Actually, it's possible that we need the long longs for this problem. So let's use long longs. And now let's go through and take the maximum. Whoops. Now obviously we could have just put this inside of here after this statement and it would do the same thing, but I just wanted to show this step by itself. So now let's output the answer. Okay, so let's try to go ahead and submit this. That is not what I meant to do. Whoops. I might have accidentally logged out. Okay, while that's loading, are there any questions about the implementation of difference arrays? This is going to take a long time, so okay, so this problem is a little bit more complex. I'll just summarize the statement right now. So it's almost like a tower defense game where you lay from one tower at specific positions. So and they have a range of cells that they can attack. So for each of the n towers, they'll attack balloons that are in the cells from Ci minus Ri to Ci plus Ri inclusive. And every second it's going to do di worth HP worth of damage to the balloons in this range. And afterwards you have M balloons that will float through the L cells that they mentioned earlier, and they begin with HI HP, and what you want to know is how far along the course each of the M balloons will make it. Okay, so if we approach this problem, we can find about two ways to do it. So you can either simulate each balloon, so you simulate each balloon going along the cells, so you loop through each of the cells, and then you check each tower, so you loop through all the towers and you check whether that tower can damage the balloon at the current cell. Or you can calculate the damage a balloon will take by going to each cell, then checking how far each balloon will make it. And we're going to take the second approach because that's easier to optimize. So let's break it down into two parts. So first we want to calculate the damage dealt in each cell by the towers. So what this means is that if I'm at a given cell, I want to know how much damage I'm receiving in this cell. And that's not dependent on the balloon, right? The towers have a certain range that they're going to attack no matter what balloon you are. All that matters for each individual balloon is their individual health points. And after that, we're going to calculate how far each balloon can go without dying. So let's first deal with the first part. How can we calculate the damage dealt in each cell by the towers? So since each tower deals a certain amount of damage to a range of cells, we can see that this part can be reduced to range increments. So what I mean by that is if I had an array where, let's say, cell at I stores the amount of damage a balloon will take in cell I, or maybe I should name this something like damage, then what I want is to find damage at I. Well, I should specify that will take in cell I by all the towers. Okay, and we can see that this is basically forming range increments for each of the towers. So we loop through each of the towers and we increment each of the, we're going to increment the Ci minus Ri to Ci plus Ri with D. And so we can use difference arrays on this. So recall that difference arrays allow us to perform range updates in O of 1. So we essentially use difference arrays to make this n squared loop an O of n loop. So the reason that would be n squared is because initially we had an O of n towers, and then for each tower we needed to go through O of L cells. Right, so L goes up to 1,000 and n goes up to 1,000. Actually, I think for the purposes of this problem, for loops might work, but for the purposes of using difference arrays, we're going to optimize that. And so if we have an n squared here, what we can say is instead of going through the O of L cells, we're going to update the ranges in constant time, and so we can have O of 1 here. And so finally this entire process would take O of n. Okay, so but after that we have to get to part 2, which is calculating how far each balloon can go without dying. And so now we want to try to combine some of the knowledge that we learned over the past couple of lessons, and now that we know how much damage a balloon will receive in each cell, how can we find how far it will go? And we want to do this in sublinear time. So does anyone have any idea? If I knew the amount of damage a balloon will take in each cell, then how can I know how far a balloon will make it along the course? Binary search, yes, that's a very good idea. Okay, so to do the binary search, the logic is this. So if we compute the prefix sum array of the damage cell, of the damage cells, or I should say the damage array, then we can see that the damage only increases, right? The balloon goes from left to right along the course. So let me just give a quick example. So if it takes 1 damage here, let's say 2 damage here, maybe 4 here, 5 here, 0, 6, and the balloon goes from left to right, like that. And so if we calculate the prefix sum array of this, what we notice is what we're actually asking is how far can the balloon go without the number exceeding that the HP of the balloon. And so the question is, let's say compute the prefix sum of damage, and now we want to know, find the largest index of the prefix sum array that does not exceed the HP. And you know that the balloon will burst right onto the next cell. And so the balloon will make it to the cell immediately to the right. It's not necessary, right, of that cell. And so finding the largest index of an array that satisfies some condition, this is very familiar to us. This is the classic binary search algorithm that will do this in log n time. And so the second part of this can be done in O of m log L. And the first part is done in O of n. Okay, so are there any questions about any of this before I start to implement this? Maybe I should give an example. Okay, so if I had a balloon with HP of 10, and I had a prefix sum of this, we know that if as it goes along, let's take the original array first. So it can go along 0, then it goes along 4, then it's left with HP of 6. So initially it had 10, then it had 6, then subtracting 1 again, it had 5, and subtracting 2, now we have 3, and subtracting 5, we have -2. And here is where it burst, right? And you can see that this is equivalent to just having this 10 on the prefix sum array and binary searching on this prefix sum array to find the largest thing that is greater than this, right? So the first element that is greater than 10 in this array is obviously 12. And you can see we end up with the same answer here. Okay. So I'm going to go ahead and implement this if there are no questions. Oh, and this problem also does this thing where it has t test cases, and for each of the t test cases, there's a unique set of test cases. So that's a little bit annoying, but how we usually deal with this is we just have in t, we're just going to take in the number of test cases here, and for each test case we're going to run it inside of a separate function. And so this is one way to solve these types of problems. So okay, so I'm going to call this solve function. And this is where we're going to put our code. And you know that when it calls the main function, it's going to call the solve function t times whatever t is. Okay, and so first of all, you know that this might run more than once. So whatever array we declare here, we're going to need to reset it to its original state. So not clearing your data structures in between each test case, that can actually mess you up a lot, which is why I kind of don't like these separate test cases and one test case kind of problems. But anyways, so let's make a difference array. So that's going to be up to 1,000. So all the variables are L, N, C, R, D, M, H, and let's make a difference array that will go up to 1,000. Okay, so at first I just want to make sure my difference array is clear between each test case. So I'm going to set all of its elements to 0 bytes. Now you can obviously just do this with a for loop as well. Okay, so now let's take in input. So okay, so for the next, so there's going to be n towers. let's make a for loop that loops from 1 to n, inclusive. And we're going to take in CRD. And you know the range is going to go from CI minus RI to CI plus RI, but obviously it's not going to go less than 1 or greater than 1,000. So let's increment the starting point. So the starting point is C minus R, but it can't go lower than 1. So we're going to say max 1 C minus R. Oh, I missed addition there. And we're going to decrement the ending point. That's exclusive. So the ending point is at most L, and that's C plus R, and plus 1 because we want the exclusive ending point. Okay, and that should be it for our updates. So now we're going to take the prefix sum array of this difference array to get the original array, and actually we're also going to have to do that again to construct our prefix sum array. So let's go ahead and do that. Don't forget to loop up to L instead of N, because your difference array goes from 1 to L because it represents the cells. And this is gonna restore the original updated array. So this is going to construct the prefix sum array. Okay. Okay, so now that we have our prefix sum array done, now we just have to process each of the balloons. So let's go ahead and let's go ahead and take in M from input, and for each of the M balloons, it's going to have a unique HP value. And so now we're going to start our binary search. So remember that we need a low point. And the low point here, even though our array is 1 index, I can make this 0 index, because if it goes down to 0, then I know that it died at cell 1, right? And that's how I'm going to know. So in the high point, I'm just going to set as L. Now remember, there is a possibility that none of the cells will, well, there's a possibility that it's going to complete the course. And so in the context of our implementation, that means that the HP value is greater than all of the prefix sums, so greater than the end of the prefix sum array. And so we're just going to check that as a condition in the end. Okay, so let's declare an int variable answer, and let's default that to 0. Okay. So while low is smaller than or equal to high, we're going to take the middle point. So mid is low plus high over 2. And this is possibly going to overflow. So should I use long longs? Maybe. I'll worry about that later. Whoops. Okay, so if difference at mid is greater than the current element, so, or sorry, not the current element, the HP value, then we need to move down, right? Can't sustain the damage, go left, so high is equal to mid minus 1. Actually, I should have done this a bit differently. So let's say instead, I'm going to do this opposite. What I did at first so that it's consistent with what we've been doing, which is having the condition be the satisfied condition. So if the HP value is greater than difference at mid, then we know that can sustain the damage, go further. Actually, let me check the problem constraints. It will pop as soon as it has taken at least that much damage in total. Okay, so it should be strictly greater than, I think. So then you want to go further, so the low point will be set to the midpoint plus 1, and the answer will be set to mid. And otherwise, the high point is going to be set to the midpoint minus 1. So what this means is it can't sustain the damage, and it wants to go back. Okay, and so after our binary search, we know that if our answer is equal to L, and the answer and the HP value is greater than diff at L, then we know that it can sustain all the damage. And so we're going to output, what did it tell us to output? Balloon leakage. And otherwise, we're just going to output answer plus 1. Whoops. Okay, let's try this. Oh, whoops. This is meant to be a plus equals. Okay, I've done something not correct. Let me see. Okay, I'm going to output my prefix sum array, actually. Okay, so let me check that this is correct. So from 3, it's gonna go from 0 to 7, so it's gonna add 1. for the value 9, it binary search and went here. So that means something must have been done wrong in my construction. X3 integers. C minus R 1 C plus R L. Will lose its final HP while that's 5. Third balloon. So, okay, I see now. So I'm supposed to be incrementing D instead of incrementing 1, because each tower is going to do D damage instead of 1 damage, which is what I assumed from the previous problem. Okay, so that would give me the correct output if I just remove my debugging output. I think, yeah. Okay, so are there any questions for how I did this problem here? Okay, no questions, then I'm going to move on to the next problem. And so in this problem, what we're going to try to do is to extend the difference array into 2 dimensions as well. So remember how we extended the prefix sum array to 2 dimensions, and that was kind of like subrectangles, adding and subtracting. Well, difference arrays is going to be a very similar idea as well. And so this problem says that they have 2D grid of squares with square 1, 1 at the bottom left, square nm at the top right, and the cake also has cake and k different icings, and each icing is going to go from xi to yi to capital Xi, capital Yi, and so this icing is just going to cover an entire subrank rectangle of the cake. And so what they're going to ask you Q times is they're going to give a query A, B to CD, and they want to ask you how many icings are in that rectangle that they gave you. So okay, so essentially it's asking us to apply range updates on rectangles and also perform range queries on subrectangles. So we know how to do this part, right? So given an array, or actually given a 2D grid of numbers, we know how to construct the prefix sum array and then use principle of inclusion-exclusion to obtain the piece of rectangle that we want. And so what we need to find out is how we can use difference arrays to do this part, which is to perform range updates on grids. So if we recall what we did for prefix arrays, so let me just draw a quick grid. So actually maybe I can use the example. Yeah. Okay, so this example we have, okay, so first of all, it doesn't matter what orientation they tell us it is. We can just transpose that to whatever is most convenient for us, because we'll be transposing all of the coordinates anyways. So this wants a 6x5 grid. So 1, 2, 3. There. Okay, I may have made this a little bit too wide, I think. Oh, I made it 6 wide and 5 down, which is actually not what I wanted, but anyways, if I wanted to update the range 1, 3, 4, 5, first of all, let's just imagine what would happen, or actually let's imagine what we did for prefix sum arrays. So if we had some numbers here, so we'd had 1, 0, 2, 3, 4, and let's say 6 here, and this was the original array. What we did for prefix sum arrays in the 2D version was that each cell stored the sum for this entire rectangle here. And so, for example, this cell would store the sum of this entire rectangle here. And so every cell stores the sum from 1, 1, which is the top left, to that current cell. So what would happen if, let me try to erase some of these. What would happen if you add 1 to one of the positions, and then you constructed a prefix sum array, or you computed the prefix sum array based on this array again? You would notice that every single one of the rectangles that contains this element is going to add 1. And so if you add 1 to this, then after you construct the prefix sum array, what's going to happen is this rectangle is going to contain it, this rectangle is going to contain it, this rectangle will contain it, and in other words, anything that is not to the left or above it is going to contain it. And so what you're actually doing is you're adding 1 to all of the elements that is in the subgrid that is either below it or to the right, and including itself. And so if you add 1 here and then compute the prefix sum array, you're actually adding 1 to all of these cells. And so how can we use this to update a certain subgrid of our grid? So we're gonna do the same idea. We're gonna do the inverse operation for whatever cells we don't want. So let's say we only wanted to update this specific subgrid. Now, using the same idea, we can say, okay, perform the inverse operation here. And so if we subtract 1 from here, that's going to cancel out. So that's going to cancel out. And if we subtract 1 here, that's going to cancel out. But we still have these left. So we also need to perform the inverse operation here. Now, the problem with doing this is once we get past these 4 cells and we start to subtract 1 for all of these as well, these end up being negative, right? And so what we do is we add back 1. So we're going to add 1 here. We're going to perform the inverse here. We're going to perform the inverse here. And since this is subtracted twice, we're going to have to add back 1 here. So these need +1s as well. And so finally, you can see that everything becomes 0 except this grid. And so in total, we need to perform 4 operations for each update. So are there any questions as to how we're going to use difference arrays for 2D grids? Okay, if not, I'm going to go ahead and just implement this. So our grid goes up to 5,000. Need a variable k. Okay, so first we need to take an input of nm and k. And then we're going to have to apply k updates. So instead of xy, I'm just going to keep using ABCD. So okay, so as we said, oh, I erased it. That's bad. Anyways, as we said, we're going to increment the top left corner. So in this case, that would be AB. So and we know that we have to subtract from the bottom, and that's going to have the same x coordinate. So that's the b is going to stay constant, but the y coordinate is going to be c. The y coordinate is going to be c plus 1. And we also need to subtract it for the one to the right to exclude all of those squares. So in this case, the y coordinate would stay the same to be a, but the x coordinate would have to add 1 to d, so that would be d minus 1. And finally, we subtracted too much for the grid from c plus 1, d plus 1 to the end of the grid. So we're going to add back to c plus 1, d plus 1. Okay, and so that should probably perform all of the updates for our grid. So now let's take the prefix sum array of this 2D grid to get our original array back. So actually, this should go up to m. Okay. And recall how we, oh whoops, I'm missing a bracket here. Recall how we construct the prefix sum arrays in 2D. So what we're going to do is to take the grid that is above it. So grid ending at the cell that's directly above it. So that would be I-1 at J. And we also need the cells to the left. So let's take the grid ending at the cell that's directly to the left. So that would be I at J minus 1. And we took too much, so we need to subtract the grid ending at I minus 1, J minus 1. Okay. And we know that we're going to have to do this twice to construct a prefix sum array, because now we want to start answering our queries. So let's take an input Q, the number of queries, and we're gonna do exactly what we did 2 weeks ago, or was it 3 weeks ago? I think it was 3 weeks ago. And we're gonna answer the queries using our 2D prefix sum array exactly the same way. So let's first take an input. Okay, and we're going to output grid at C at D, except we have to subtract whatever is left of A. So subtract grid. Wait, CD is the bottom right corner, right? I think so. So whatever is above A should be subtracted. So okay, let me just draw it out again, just so we can visualize this process. So if I had this point A, B, and I had this point C, D, and I wanted this rectangle here. So let's divide this into regions. So we're going to take this whole region. That's what grid at C at D is. And we need to subtract this region right here. So we know that, so by the way, I'm using y comma x coordinates. So we need to subtract this rectangle right here. And so that would be the y coordinate A minus 1 plus the x coordinate, that's D. And we also need to subtract this rectangle right here. So this rectangle here. And that would have an x value of B minus 1 and a y value of C. And we know we subtracted too much in this region right here, so we're just going to add back the region right here. So that would be grid at A minus 1, B minus 1. Okay. Okay, we can see that that worked. Are there any questions as to how I use 2D difference arrays to update subrectangles? I can summarize the key idea, which is if you have a rectangle that is, oops, it's not drawing, and you want to update a certain subrectangle, whenever you add anything to a certain position, think about what you're going to be doing after you perform all your updates. You're going to be taking the prefix sum array of this difference array that you're taking right now. And so if I wanted to update this specific rectangle here, what I can do is, well, let's just be a bit more specific, which is to add 1 to this entire region here. We can add 1 to this entire region here, and then we're going to subtract 1 for this region, or sorry, we're going to subtract 1 for this region, and we're going to subtract 1 for this region, right? Because every time you update +1 here, that's going to affect this entire region. And so if we do a -1 here, that's going to affect this region right here. If we do a -1 here, that should be a plus. Oops. If we do a -1 here, that's going to affect this entire region. And so this thing right here would be +1, -1, -1, that would be -1, but we don't want to negatively affect this region right here, so we're going to add back the 1 right here. And so this tile remains unaffected. And so finally we will have this region updated. Is that clear? Okay, so all of this code is going to be on GitHub a bit later, and I did put some practice problems in the doc, so if this thing is gonna load anytime. Okay, so I skipped this problem because I think it would be good practice for you guys to go ahead and do on your own, and you can try some of the practice problems. And they might involve some techniques that is not just difference arrays. There might be, not sure whether it's binary search or can't remember what I put on there, but just keep in mind there might be more techniques involved. And yeah, try some of the practice problems either on difference arrays or whatever ones we did before. And yeah, that'll be good practice for the contest. That's going to happen presumably on the 24th, but yeah, we'll have the next 2 weeks off, so you'll have lots of time to practice. So yeah, are there any questions? And if not, I think this is a good place to end the lesson. Thank you for coming. Have a good day.